at BTRY, we want to develop a battery which is not seen as a limitation, but rather as an enabling technology for next generation electronic devices. Batteries are really the secret hero of today's electronics. They enable communication, they enable the use of renewable energy, but also applications such as electric cars. But nevertheless, even they had a very long journey since the 90s, there are still only two energy storage solutions which can offer either lithium-ion battery, which can offer high rate, or capacitors which can offer high energy, or capacitors which can offer high rate. But there's still no technical solution which can combine high energy with high rate in the same device. This is what we are working on to change. We're developing a solid-state battery based on semiconductor fabrication methods, which allows us to build a thin battery which we can stack on top of each other, and this allows us to build a battery which has a high energy and a high rate performance. It can have C rates up to 60 C, so you can charge it in just 1 minute. It can be ultra thin to be integrated into applications such as a credit card, and it can operate at an extended temperature range. How do we do it? Here you can see what a typical solid-state battery looks like. You usually have thick electrodes, such as a cathode and an anode, with a separator. And because the electrodes are thick, it needs time that the ions and electrons travel through the whole cathode. And this time limits the rate performance. Thin batteries, on the other hand, they're very thin, and so we can have very high charging and discharging rates, but since you have not a lot of energy per area, the energy is low. And what we do is we can stack these thin films now on top of each other. On top of one substrate, we can have several of these cells, and by doing this, we can have high energy and high rate. Nice. There's one key difference. We use vacuum processing to build these batteries, where traditional, usually it's liquid processing. Vacuum processing has established processes in many industries, such as OLEDs, for example, where they worked for 10 years to replace liquid processing, replace vacuum processing with liquid. So far, not successfully. So this is still a very widely used technique. Also, it uses for solar and semiconductors. It is especially important if you need very high quality films with a precise control of the thickness, what we need, especially if we grow these on top of each other. That's it. Now, what have we contributed to thin film batteries? So I will quickly share you what work we have been done before incorporating the startup. One is we have worked on the cathode. So typically, thin film batteries are done with lithium cobalt oxide cathodes. We have worked on changing this to use NMC 811 cathodes in our films. And here you see just the cycling performance of one of these cells, which in this case has a cycle life of about 900 cycles at 4C, so relatively quickly charging and discharging. We are able to produce them anode-free. That means that we don't have an anode as we fabricate. So during the fabrication, we have a cathode, we have the separator, but no anode. The whole lithium for the anode is in the cathode itself. And for this, we need very homogeneous growth of this lithium metal. So it's really growing and dissolving again in the process of charging and discharging. And this is what you can see here. You have a current collector, you have a solid separator. And in between, there should be the anode. In this case, there's a small interfacial layer which we added. And this allows now that we can very homogeneously grow lithium metal. And you can see here, this is a plated lithium metal without applying any pressure, as is typically done with other solid-state batteries, and at room temperature. And we can completely remove it again. And we can do this at very high speeds, allowing that the battery can still be charged and discharged in just 1 minute. And we have demonstrated the twin stack. So what you see here is we have a substrate, and then we have two cells, each with a cathode and an anode, directly on top of each other. And we can do this because we use a semiconductor fabrication method, and you see this is a very thin layer, so they have to be very precise, that there's no pinholes between them. And if we do that, we can build a battery which has two cells directly on top of each other, and these are now electrically connected in series, which means that the voltage adds up. What we can see here, we can probe the individual cells, and if you probe the full battery, we see that the voltage has doubled, and in this case also the energy. Now, this has all been done in the research group, so meaning that we had very small areas. This is typically what we worked with. This is just a few square millimeters in size. Since then, we have spent a lot of effort on scaling this technology. This has all been done still on the research laboratory scale. At the research laboratory scale, we were able to scale this to about 10 by 10 centimeters, which is the biggest which we can do in the research lab. But this is already 1,000 times greater area what we had before, and also we improved the processes to increase the speed. And this summer, we have been in California to rent the first pilot production machines, and we're able to fabricate on much larger areas these batteries. And we're continuing in this path. We're having the next pilot production scheduled for this winter to produce in even larger areas. Now, what is the battery which we're actually producing right now? And as a first product from our startup is the BTRY 1S4P. And you can see the characteristics here. It's designed to be integrated into a device such as a card, a credit card, or any other card label type device. It's flexible. It's very thin. It has a capacity in the order of 50 milliamp hour, which is enough for most sensor applications. But importantly, it has a very high power ratio. So it can, in this case, 500 milliamps with the same battery. And this allows that you can measure signals, but you can also send signals for different protocols, for example, LoRaWAN. And at the moment, there are many devices or companies which actually use a battery and a capacitor to have both the capacity and the power. And we can combine this into one device. It's very light, it's very thin. The whole cell would be in the order of 0.1 millimeter thick, and it has an extended temperature stability, so you can laminate the battery into a device. How does it perform today? At the moment, you can see results from our cells where at the moment we are at 500 cycles if we cycle at 20 C, so 3 minutes charging and discharging, very fast charging and discharging rate. We're already at 500 cycles. We can charge in 1 minute, not full capacity, but if we charge in just 1 minute, we already get 40% of the full capacity inside of these batteries. And if we had 5 minutes, we're above 80%. And here you see the current performance, so we can achieve this 60 milliamp. This was, in this case, from a customer asked to this their protocol for sending LoRa signals. And we can do this with a cell which has little capacity, but already has very high C rates to have the power for peak performances. Who we are, we founded this company together, Abi and I, in April last year. We're both scientists from training, physicists and chemists. We have been in academia for a while before starting the startup journey, but we have also educated ourselves in entrepreneurial leadership. And yes, before that, Abi was a PhD student working on the core technology. He's also here this week, and I've been leading and coordinating research projects. We're a team of 9 people at the moment, and 2 other key hires which are also with us today at Electronica is Geronimo, responsible for business development and commercial operations, with background in consultancy and a fintech startup, and Miguel, battery engineer, which has previous tech startup experience. We have a few advisors. One will be announced soon. He has already successfully scaled a battery company within Germany and recently exited operational. What we have achieved so far, we have incorporated in April last year. Since then, we've raised 2 million funding. We have sold first batteries. We have secured first pilot projects. We have scaled our prototype from just a few square millimeters to several hundred of square centimeters. And we have demonstrated an anode-free solid-state battery on a flexible foil. And we demonstrate that we can charge it in just 1 minute. What is our timeline? We would like to bring this technology in the market as quick as possible. We estimate that it will take up to 4 years to really reach TRL 9. Already today, we do the first production tests with machine producers, and we aim to have our first pilot production next year in order to have a serious production in 2 to 4 years, roughly, time. That's it. Today, we still have a small battery, but we see that there are many possibilities for such a battery technology, and I'm very much looking to see what the conference will also tell us, where potential use cases are. Thank you.
Now, second place with a marketing budget of €25,000 from Elektor this year at the Electronica Fast Forward Awards is BTRY, and this will be presented by Brian Tristan Williams from Elektor. So, Brian, you've been here all week and seen our innovative startups presenting. What do you make of the startups themselves and the startup community, and why is it so important for our industry?
Well, working with startups it's such a difficult choice to make because they're all so innovative and all doing such amazing things. So it was tough. We had a tough deliberation 2 years ago, and we had a tough deliberation this time. But I'm glad we get to recognize the overachievers that you all are.
Fantastic. And what do you find exciting about the BTRY solution and where that's going to take our industry?
Well, I also called it BTRY, but I was informed that battery is fine. So everyone needs batteries. Batteries are everywhere. There's one there, there's one there, there's one there. So they have ultra energy dense batteries in a small footprint using advanced semiconductor techniques, and that many thousands of times rechargeable, and apparently in 1 minute, which I'd love to see, because we all know being stuck tethered to a wall waiting for something to charge. So I think it has the potential to revolutionize the industry because, as I said, everything needs a battery. So if you guys come right, it's a revolution.
Fantastic. Well, if you pass me over the microphone, we're going to get your check-in to view and get a photo of the team together here on the stage. Photographers here at the front. So there we go. Congratulations and a round of applause, please. So, take your check with you, make yourselves comfortable and think about how you're going to invest that into the next steps of the startup. Congratulations.